Okay, yeah, thanks a lot for this invitation. This is first time I'm coming to Bangalore, ICTS. And when I reached ICTS, it didn't look like Bangalore. And after reaching ICTS also, it doesn't look like Bangalore. Okay, so this is the talk of the title. The title of the talk, Periodically Driven Langevin Systems with Vanishingly Small Viscous Drive. This is a work which is done with my former student Shakul Lavasti, and the reference is given here. Okay, so let me explain. Yeah, so I'm generally interested in periodically driven thermodynamic systems. So basically, you take a thermodynamic system and shake it periodically, or drive the temperature periodically, and then what we expect is that the system in the large time probably will have some stable in the sense time periodic behavior. And if it is stable and if it has this time periodic behavior, then that is what I'll refer to as oscillating states. Okay, so it's a state which is different from, of course, equilibrium, steady state. And in general, I'm interested in what are the properties of this particular oscillating state. So this typically when you so the macro variables of a thermodynamic system, they behave. I mean, they are governed by Langevin dynamics, more precisely overdamped Langevin dynamics. And if we drive the system periodically, then we expect that they are also driven. They are also governed by some underdamped like Langevin dynamics. Okay, so the prototypical example of this underdamped Brownian particle is a driven underdamped Brownian particle. And so this particular, yeah, so this is a summary of what I'm going to talk about, in fact. So this particular, you look at this particular, this Brownian particle, it's parameterized by viscous parameter, noise strength, and some potentials. So these these parameters, if you make them time dependent and periodic, then that is what I refer to as driven. Okay, so there's only one time period, the one driven period. And then what I'm interested in is what is the large time behavior of the system. So if it is periodic, then and it's stable, then I'll refer to it as oscillating state. Okay. So if these parameters are undriven, then in the large time limit, we know it becomes an equilibrium. This particular, the distribution is the equilibrium distribution. And it is only governed by the temperature, bath temperature. So it's the ratio between D and gamma. So if it is, in this particular, if these are driven, then clearly it cannot be characterized by this alone. It is characterized by even gamma is included. So in general, we were interested in what is the dependence of this particular oscillating state on this gamma as you change gamma. Okay, so what are the properties of this oscillating states for given TB, this bath temperature, and as you take this gamma going to 0. So in general, this vanishing viscous limit it turns out it's a singular limit, and it's actually a difficult limit to in general, it's a difficult limit, but it turns out in these driven cases, we have a way of figuring out what is the singular perturbation theory. So what we find is that there are two classes in the limit gamma going to 0, that you will see that this oscillating state, it actually, there are two distinguishable classes, where it turns out when one of the classes, it looks like an equilibrium state, and the other one, it doesn't. Okay. So let me give a few more details. So the underdamped Brownian particle is governed by a Fokker-Planck equation. I mean, it's a Langevin equation. So this is gamma is a parameter, D is a parameter, and then there's this force, which you can have, for example, harmonic parameter, and you can have various other, anharmonic parameters. And so if these are, like I said, if they are undriven, then this large time distribution is an equilibrium distribution. So, so if you choose to drive these parameters periodically, then we show that, in fact, we have shown in earlier work that, that under certain conditions, this, the large time distribution exists. So the limiting distribution exists, is stable. And so this particular system actually supports these oscillating states. So the way we define oscillating state here is that you take t going to infinity essentially, and if it exists, then we say it's a this oscillating state. Okay. So the question which we have been interested in is this low viscous drive. So there are various reasons why one should be interested in this. The inertial term turns out to be important, so one has to look at underdamped case. And this is the limit where velocity doesn't decouple from the position. And also the effects of the drive are quite drastic in this particular case. So that is the reason why we wanted to look at this particular limit. So all the parameters have been, so there's a one parameter extensions of these viscous parameter and the noise strength, in such a way that the TB, the bath temperature is kept constant, kept fixed actually. So it's a time dependent quantity, and we would like to understand what happens when alpha goes to 0. Okay. So it turns out that alpha going to 0, the Fokker-Planck equation becomes Liouville equation. So Fokker-Planck equation, in general, I mean, this particular equation has a unique solution, no matter what initial condition you start with. When you look at the last time asymptotic solution, that's unique. On the other hand, Liouville equation, that is not unique. In fact, it very much depends on the initial conditions. The limiting case doesn't exist in general. So these two limits, they don't commute. And when we do the usual perturbation theory, the set of the hierarchy of equations that we write down, the first 0th order equation is actually a Liouville equation. So in other words, we don't have a solution for that. So the standard perturbation appears as if you're taking this particular limit first and then t going to infinity, and which is not what exactly we want to do for identifying this oscillating state. But and what I suspect is this is probably, I mean, in fluid dynamics, for example, inviscid limit is essentially this, and probably the reason why we don't understand turbulence as much as we desire is because we don't have control on this particular limit. But fortunately, in this case, there is a nice control which we can have. Okay, so I'll probably take a minute. So there's an alternative way of identifying this oscillating. There's an alternate way of identifying this oscillating state, this large time limit. So you take an arbitrary solution and demand periodicity, right? And if the Fokker-Planck equation has a unique solution, this demand essentially identifies that unique solution. Therefore, so basically follow the standard steps. You have this Fokker-Planck equation, which is of this form. Do the standard perturbation, solve this hierarchy of equation, not knowing what this initial distribution is. So essentially, we are trying to choose the initial conditions such that we end up getting a periodic solution. So the identification of this is done by demanding this periodicity of this potentially. So, and then we impose this periodicity condition. So essentially what happens in the perturbation theory, if you demand periodicity at the order nth level, then the order n-1 is completely fixed. So that's how we identify this particular distribution. So this particular algorithm, of course, can be employed even at the level of moments itself, moment dynamics, and then find out the moments and then write down the oscillating state distribution. So I'll probably wind up in half a minute. So, in fact, so just to give the result, if you choose a simple potential, harmonic potential, so it turns out that if this condition is if this condition is satisfied, then when you look in the limit t, in the alpha going to 0 limit, turns out the oscillating state actually is an equilibrium distribution. That's what we get. So essentially, you can imagine being in a, where bath temperature varies, or being in a place where the nights are cold, very cold, and the days are hot, very hot. Then this particular scenario essentially tells that it's possible to have a comfortable indoors. Okay, so there's also, I mean, if this particular condition is satisfied, I mean, if essentially if this particular parameter here, it is harmonic, it syncs with the time period, then it turns out that the oscillating state in this particular limit is, again, it is periodic, but it has a periodicity which is a fraction of the time period. And when you switch on small alpha, then this particular time period goes back to the standard time period. Yeah, so these results are not restricted to this particular potential. In general, they're broader than that. Thanks.
Questions?
Near oscillator, which you're also driving with a time-dependent force. I mean, so is it obvious that you'll always get a unique solution? So I'm thinking like in the zero noise limit, for example, if I take a Duffing oscillator or something, for given parameters, I can have multiple like...
in the zero noise limit,
yeah, in the zero noise limit, at least I can have either a chaotic solution or a periodic solution for same parameters, right? I can have multiple attractors. Yeah. Now, if I switch on noise, it's not obvious that I'll get a...
So what I am assuming is that there's a unique periodic oscillating state.
Right, yeah. So is there a proof for that? I mean,
so this particular, in fact, earlier work which we have done, what we have showed is that if you take a harmonic oscillator, right? If you take this particular harmonic oscillator, this force, then it turns out that this particular problem has an underlying SL2R symmetry. And so we actually exactly solve this problem to show that we have a condition as to under what conditions the large time limit exists.
Okay, so even for harmonic, it's not always guaranteed.
It's not. So this problem essentially, it's like, it's the same thing, band theory. So the problem we could solve exactly in the sense that we could map this problem into a Hill's equation. And the Hill equation is like a block equation, which exactly tells you that for not all energy eigenvalues, you have a,
okay,
it's not allowed, right? Yeah. So it exactly turns out, for example, if you keep changing this gamma, it's not clear whether oscillating state exists or not. But if it exists, then it's stable under any perturbations. That also can be we solved it exactly. Okay. Right? So for that, we are assuming that those conditions are respected, in which case this is.
Typically, when we have this periodic, drives, there could also be lag between the drive and this.
Yes,
is there something you
have? Yeah. I mean, so I did not give any details. In fact, I didn't say any results here. But we have a solution. So basically, we looked at what are the kind of drives you can have, and for example, what is a lag in the system temperature and various other quantities.
So if there are no more questions, let us thank the speaker.
Yeah, thanks.